Welcome back to Probability and Statistics 1. This is Unit 3 on discrete probability. If you think about it, all the examples we've looked at, and we've looked at quite a few examples up to now, have been probability models where we've had finite sample spaces, and not only that, but sample spaces in which all the outcomes are equally likely. That's sort of the definition of a simple random sample, for instance, right? It's a sample from a finite population that has the property that all samples of the same size are equally likely. We did actually in the very first lecture look briefly at a model with a countably infinite sample space, but we didn't define any probabilities on it. We just looked at the sample space. You'll remember that was the model where we tossed a coin until we got the first head. So the first head could occur on toss 1, or it could occur on toss 2, 3, 4, and theoretically it might occur on toss a billion. So the possible outcomes form a countably infinite set in that case, right? Just the integers. Probability models that are either finite or countably infinite are called discrete, and they have a sort of unifying thread to them that enables you to describe them in a comprehensive and sort of unified way. And so we're going to talk about these kinds of spaces first. And we'll introduce some basic and fundamental notions to the further development of probability theory in the context of these discrete spaces. And we'll later on, when we move to continuous spaces, we'll generalize those concepts to the more general setting of continuous spaces. So these are concepts like random variable, expected value, conditional probability, independence. We'll introduce all those concepts in terms of these discrete probability models. So the main thing about a discrete probability model is that the sample space is either finite or countably infinite. And it turns out that you can describe these models completely, basically, with what's known as a probability mass function. So if you've got a discrete space, S, and you have a function, little p, mapping S into the reals that satisfies these two properties. First of all, P of S is at least 0 for any outcome in S, and the sum of P of S over all outcomes, S in big S, is 1. Such a function is called a probability mass function. Now what the probability mass function represents is the probability of individual outcomes. So if S is an outcome in S, P of S represents the probability of that individual outcome S. Of course, probability measures measure probabilities of more than just outcomes. They also measure probabilities of events, which are collections of outcomes. But we can build a probability measure out of a probability mass function, as you see here in the second bullet. If you take any event, E, any collection of outcomes in S, and compute the probability of E by simply summing the probability mass function across all outcomes in E. In other words, we're defining the probability of an event E as the sum of the probabilities of all the outcomes in E. Then it turns out that probability measure, capital P, is going to satisfy the axioms of probability, those 3 axioms we saw in our first lecture, first unit. So that leads us to theorem 3.1. The P, defined as you see above, is a probability measure on S. And this theorem basically says that given a probability mass function, which gives probabilities of individual outcomes, you can actually induce a full-fledged probability measure, which gives the probability of any event, and you do so in a simple way. You get the probability of an event by simply summing the probabilities of all the individual outcomes in the event. And those probabilities are given by the probability mass function. So this means that we can understand discrete probability spaces through an understanding of their probability mass functions. Here's an example. Consider the process of tossing a pair of fair dice and recording the value on each. So we've seen this before. We've seen the sample space has 36 outcomes in it. There you see them. They can be represented as ordered pairs. I is the value on the first die, and J is the value on the second die. Since the dice are fair, it seems reasonable to assume that these 36 outcomes are all equally likely. So in this case, the probability mass function would just be a constant function, right? P of S, where S is any outcome, would just be 1 over 36. And that's because all the outcomes are equally likely. Since there's 36 of them, they all have to have probability of 1 over 36. And then you can use that probability mass function to compute probabilities not only of outcomes, but of ends. So for instance, the probability that the sum is 7 would be the sum of those, the probabilities of those 6 events you see there. And so that'd be 6 times 1 over 36. Similarly, the probability that the die are equal is also 6 out of 36. And the probability that the first is 3 more than the second would be 3 out of 36 because you have those 3 outcomes. So these are the kinds of models we've been dealing with up to now. They're called equally likely models, or discrete uniform models is another term for it. In a discrete uniform model, you've got a finite sample space, and the probability of each outcome is equal in that sample space. And so it has to equal 1 over the number of outcomes. We've seen this before, theorem 3.2. If you have an equally likely sample space, a discrete uniform model, then the probability of any event is going to be just the cardinality of that event divided by the total cardinality of the sample space. And we'll use this abbreviation for a discrete uniform model on a sample space S, just uniform on S. And let me end with a little question for discussion here. Is it possible to have a discrete uniform model on a countably infinite sample space? If so, show me an example, and if not, explain why no example is possible. We'll leave it here for today. When we come back, we'll start looking at more discrete probability models, including models on countably infinite sample spaces, and we'll start talking about some of the basic properties of such a model. All right, we will be back at you real soon. In the meantime, y'all take care.